is Science Max, Experiments at Large. Science Max!
Ha! Greetings, Science Maximites. My name is Phil, and this is Science Max Experiments at Large, and this is a syringe. You might know syringes from when you get a needle at the doctor, but syringes are used all the time in science because they let you measure very precise amounts of fluid. Now check it out. You push the plunger down, and it comes out the top. Or you could pull the plunger in, and it would suck more fluid in this way. But check this out. I've got a syringe attached to a hose here, and this hose is filled with water. And I wondered, if the hose was really, really long, how hard would it be to push this plunger down? Of course, I don't know where the end of the hose is because it was really long and I had to string it all the way around, so, here it is. Okay, so let's find out. Push the syringe down and water will come out the other end of the hose. Pretty cool. You see, this is called hydraulics. Hydraulics is a branch of science that deals with fluids like water. But hydraulics are also a mechanism used in a lot of machines. Check this out. This is a syringe with a short hose on it, much shorter this time. And I press down on the plunger of the syringe and water comes out. And I pull in on the syringe and water goes back in. Because the plunger is airtight, it allows me to push or pull the water. But what if I close the system and take another syringe and attach it to the end of the hose like this? Well, then, if I push this plunger in, this syringe fills up with water. And then I pull this plunger out, the syringe empties. So check it out. This plunger raises and lowers based on what I'm doing with this plunger. And you know what that means? We've made a remote control. Huh? Check it out. So, if you take two syringes and you take a hose and you attach them to something you want to remote control, voila, you can build something like this. We have made our very own robotic arm that you can power remotely with hydraulics. Pretty cool, right? If you want to build one of these yourself, here are the materials you need. First, you need two supports and the arm. I used pieces of wood, but you can use wooden spoons, rulers, or pencils. You'll need some craft sticks, elastics, and a paper plate. And of course, two syringes and a hose, which you can get in an art supply store or a hardware store. Here's how you build your own hydraulically powered arm. First, make the base by tracing holes for your supports the width of a craft stick apart. Cut out the holes and use a craft stick and elastic to secure the supports underneath the plate and on top. Then add some elastics and a piece of craft stick in the middle so the supports won't scrunch together, because we are holding this whole thing together with elastics. Then get your syringe in there and keep it propped up with more elastics. Then get your arm and slot it in between the supports. The arm should be horizontal when the syringe is half full. Elastics to attach the arm and the syringe. Then push down on this end of the plunger and, ha-ha, you have a remote-controlled robotic arm. You can also max it out even more by adding more degrees of movement. You can make the arm rotate side to side. You can even add a little claw attachment at the end and power it all using syringes. Haha, science and hydraulics. So let's max it out. I just need an expert to help me. Let's see. And over that way. Chris from Logix Academy, of course. Logix Academy knows all about building robot stuff. I'm sure Chris can totally help me. Let's go. Come on.
Oh, hey, Phil.
Oh, hey, Chris from Logix Academy. Great to see you.
What took you so long?
How long was I gone?
And what's with the orange lab coat?
Oh, it happened again. It keeps changing the color of my lab coat, but this time, Chris, I prepared for it, and I wore another lab coat. See?
Blue?
No! Well, you know what? This is happening a lot, Chris. So I wore another lab coat under this lab coat. I'm gonna have to wear a lot of lab coats, though, because this is happening all the time. We should talk about hydraulics, right?
Okay, yes.
Yeah, because we got some cool stuff planned. Okay, so we're just gonna get the table in here. Whoa, okay. This is the hydraulic arm. Check it out.
Oh, very cool, very cool.
If we want to max it out, what can we do? We could make it bigger, we can make it
What if we did it so that the force you put on this side gets multiplied so that this side's even stronger?
Ooh, what do you call that when that happens?
Force multiplier.
A force, I like that. Force multiplier, it sounds like a video game. So we would have a lot more power.
You have a lot more power, which we can do fun stuff.
Yeah, so if we had like lots of power, what would we do? We'd like crush something.
Yeah, let's crush some stuff.
Yeah, we could crush some stuff. Okay, can we start with syringes though?
Yep.
And then we'll work up as we go.
I like it.
So what do we need? Do we need different sizes?
So yeah, I was thinking we need a small...
A delicious plate of cheese and crackers, my favorite snack. But these crackers are pretty salty, so I should probably pour myself a glass of water first, huh? No, my cheese and crackers! Why? Why does this happen? Why does the water stick to the glass? Well, because of science. And the reason why it happens gets a little complicated, but it boils down to this one simple thing. Water likes to stick to things. Huh? Did you see? Did you see how it stuck? No, of course you didn't. You know why? Because it only sticks on a small scale. See those drops of water? That's water sticking to the surface. But it only works when the surface tension of the water is less than the force of gravity, which is why water drops fall when they get bigger. So it sticks to things. That still doesn't explain why you can pour water out of some containers without any drips, and other containers make it nearly impossible. It's all about the angle. Water will flow very easily when there isn't a large change in direction, like around the curved top of this glass. But when there's a big change in direction, like at the mouth of this teapot, the water can't make that turn as easily. This is also why pouring from a full glass is much messier than one that's less full. Pouring out of a full glass, the water only needs to change direction this much to flow down the side. But from a half-full glass, the water would need to change direction this much. So all this happens because water likes to stick to things. So let's do an experiment and coat this glass with hydrophobic spray. Now, hydrophobic coatings repel water. So if it's repelling the water from the outside of the glass, will we still have the same problem? Well, let's find out. Hydrophobic coated glass, non-hydrophobic coated glass, or just regular glass. Water likes to stick to surfaces, but it can't stick to one coated in hydrophobic coating. That's impressive. Should we try something else? Well, that's one way to solve the dribbling glass problem. Except you can't coat your glasses at home with hydrophobic coating because it's not good to eat. The secret is using a container that has a very sharp angle between where you're pouring the water and the underside of the glass, like this jug. And there you go. Now I can enjoy a nice glass of water with my cheese and crackers. Oh, right, I am. Wait, hold on, I will remake the crackers into, see, look, see, it's fine. It's fine, I'm not really gonna eat that, I'm just kidding. Chris and I are maxing out our hydraulic crusher.
Yes, before we get to that, I have a little game I want to play.
Okay, great.
Great. You can pick either the small one
The big one!
Okay.
So what's the game?
Simple thumb war. I'm gonna press down this side, you press down that side, we'll see who wins.
Okay, ready?
Yeah.
1, 2, 3, go! Oh, wow, that was really tough. Why was that so hard?
Well, Phil, I'm just really strong.
Wait a minute. My turn. Okay, 1, 2, 3, go! Yeah! See, pushing down on this one is way easier. You wouldn't think that the small syringe would be easier. Why is that?
The reason for it is that you have to push this one down a lot farther than you have to push this one down.
Let's see.
See how far this one goes, and this one's barely
This one
moving?
travels much more. This is how we can exchange a little bit of force over a long distance.
That's right.
To a little bit of distance at a lot of force.
That's exactly right.
Just like the lever, it's a mechanical advantage. But in this case, it's hydraulic advantage.
That's right.
Chris and I push down on small syringes, which gives us more force on our larger syringes. Our crusher was ready to go. Ooh, how about an orange? 1, 2, 3. We squeeze down and... Then we tried a walnut. Are you allergic to nuts?
I am not.
1, 2, 3. When we tried a golf ball, we reached the limit of what our plastic syringes and our hands could do. We need to come up with a stronger, more awesome crushing machine using hydraulics.
That's right. I have some ideas.
Okay, good. We can use metal.
We can use metal.
And we
can go bigger as well.
Ew, this water is gross, but I'm gonna drink this water. Why? Well, because of science. No, but I'm not gonna drink the water like this. First, I'm gonna use the power of science to help me clean it. How? By using gravel. Gravel, yes, gravel. So, say I've got some dirty water, and there are particles floating in that water. Large particles, your rocks, your wood. These styrofoam bits will act as the large particles. You pour it into the gravel, and the large particles get filtered out. See? Nothing but clean, clean water. Yeah, I know what you're thinking, Phil. That's not really clean yet. That's because we haven't done step 2, sand. Sand? Yes, sand. Let's say that these plastic beads are small particles. That filters out the tinier stuff. There, huh? Clean, right? No, it's not very clean. So we filter the water in the next step with charcoal. What? Charcoal? Yes, charcoal. Charcoal works just like gravel and sand, except on a microscopic scale. Say these bits are tiny particles you can't even see. The charcoal catches these like the sand and gravel caught the larger particles. This is called a gravel, sand, and charcoal filter. The gravel catches the big particles, the sand the smaller ones, and the charcoal the microscopic ones. These kinds of filters are used all over the world to clean drinking water. Ah. Delicious. Science.
Max Historica.
This is Archimedes.
What? Who said that?
It's me, the narrator. We're doing a segment.
Oh, well, I was working. Don't sneak up on a guy like that.
This is Archimedes, an ancient inventor and one of the greatest scientific minds ever. One of his famous inventions was the Archimedes screw, which was used to make holes in wood.
No, that's not what it's for. It's for water.
Right, used to make holes in water.
What? No! Look, did you even do your homework?
Hold on, it's here somewhere.
Look, I'll just show you. You see, in ancient times, we had many uses for something that could lift water up. From a well, or to take lake water from the lake and put it into a farmer's field, and that sort of thing.
Okay, I've got it from here. So, Archimedes invented a screw, and he drilled a hole in the side of that container.
No. Look, just sit down. I'll explain it, okay?
I am sitting. I'm in a voiceover booth.
Good for you. Now be quiet. Now look. What you do is you put the screw in the water like this, and then you want to raise the water higher, you see? And so turn it around like so, and the water fills each gap in the screw, and it starts to come up. It gets to the top, and look at this. Look, we've got water coming at the top there. The water is being pumped up. It is the first water pump.
I see. Still seems like a lot of work to fill a glass, but it's very cute.
No, we made them bigger. We obviously were not going to make them this big. This is not very useful.
Right. Archimedes, one of the greatest scientific minds ever. Chris and I are maxing out a hydraulic crushing machine. We tried one out of plastic, but now it's time to make one out of metal. These are called hydraulic cylinders, and they work the same as our syringes. Small ones on this side with a lot of travel, and then a larger one on this side to multiply the force. And some mechanical advantage with a lever to help us push even harder. We tried crushing a watermelon, and it worked great.
So what else do you want to crush?
We crushed a coconut.
It's cracking. Oh, there we go. Oh, it's gonna leak.
And then a can of pop. Science Max Cola, now in the new, smaller can.
Let's really challenge this press. Perfect.
A piece of wood. We tried to crush the wood, but we weren't able to get it to budge. So it's time to max it out even more.
I think we're gonna need like a multi-story industrial-sized hydraulic press.
You know where we can get one of those?
I do.
Awesome. This is water. Things float on water, like pool noodles and wood and toy boats. And now we're gonna do an experiment with how paint floats on water. How's this supposed to work again? Oh! I'm supposed to take the paint out of the can first. This is a fun experiment you can do at home. All you need is a container, some water, and paint. But not just any paint, special paint you use for hydro dipping. That's hydro, meaning water, and dipping, meaning dipping.
Carefully pour the paint on the water and add a few different colors. Then take a stick to swirl it up into a pattern.
Then you get something you want to paint, and you carefully put it in like so. But don't pull it out as soon as you get it in. You have to spread the paint away because it'll stick when you bring it back out. And then when you pull it out, whoa! Hydro dip. Let that dry, and then you have a very cool painted toy. Let's do some other stuff. This is a bike helmet.
If you put tape on what you're painting, you can remove it later to make parts that aren't painted.
Skateboard. Whoa! Oh, that's pretty cool. Now to max it out. Hydro dip pants.
Wearing the pants when you do this is super messy and not something you should try at home. But the results weren't bad.
Science pants! Science pants! Science pants. One of the ways you can experience the power of water is watching it wash away dirt. You can experiment with this yourself by making your own erosion table.
To make your own, fill a plastic tub with sand and tilt it up. Cut a hole in the tub at the low end and put a hose with a trickle of water at the high end. Then to complete your model, fill it with
A little happy town.
This small model shows how rivers cut their course to the ocean by following the lowest point. Try to design your town and the layout of the ground so the river goes around the buildings.
I'll see you later. I'm gonna take a swim in the river now.
There are lots of ways to experiment. Change the amount of water, or the steepness of the angle,
Look at the soil, it's all getting eroded over here.
or the way the town is laid out.
Every time you do it, the river goes in a different direction.
And have fun.
Oh, phew, I'm tired. I'm just gonna lie down.
And that is the power of water.
Chris and I are maxing out a hydraulic crushing machine.
What about this? Is this what we're gonna use?
We went to the Natural Resource Canada's CanMet Materials Laboratory, which is a federal research lab.
Oh, this is good. Oh, look at that!
Oh.
Is this what we're using?
No, Phil,
Oh,
it's
I can
actually-
use this. Hold on, let me figure this out.
Maybe later.
Really?
It's just over here.
CMAT is the largest research center in Canada dedicated to metals and materials research.
This is
Oh,
it. This is
yeah, right! Hydraulic press. How much force does this apply?
it. This can do 2 million pounds,
That's over 900,000 kilograms.
which is about 20 cars.
Let's crush some stuff! Oh, crushing! We gotta get the stuff.
We started out with the piece of wood which defeated our last press.
And go!
That sound.
Reversing!
It turned our wood into a pancake.
Whoa, totally flattened!
So it was time to try some other stuff. We crushed a ball of plasticine.
That is neat. You sort of made a rainbow.
Yeah.
Aluminum foil.
Aluminum foil.
Yes, it is now a solid plate of aluminum.
And a basketball.
Basketball. Good thing we got these earplugs in because when it pops, it'll be loud.
What?
Never mind.
This hydraulic press was so maxed out, we had to think of the toughest stuff to crush. We crushed hockey pucks, a safe, we crushed a hydraulic jack with the hydraulic press.
This is a metal vise. Hard, strong,
Yeah, steel.
heavy, steel.
Whoa, look at it bend. Wow.
Now it's time to crush a bowling ball. It totally exploded. Science Max, experiments at large, hydraulics. Whoa. Nicely done.
So fun.
I should reverse it and we should start cleaning all that stuff up,
Yeah,
huh?
I think so.
Okay, reverse. Greetings, Science Maximites. My name is Phil. And I am Opposite Phil. Opposite Phil. That's right. Blue lab coat, yellow shirt, evil mustache. I see. Anyway, we're looking at opposing forces today. That's forces that make things go down and forces that make things go up. Right, things with more density and things with less density. Gravity and the opposite, which is anti-gravity. Anti-gravity isn't really a thing. Well, I have to do the opposite. Right. Buoyancy. And buoyancy's opposite, which is girlancy. No, girlancy is not the opposite of buoyancy. You know, you're not helping. Right, not helping. Opposite. Haha. Hello. Goodbye. Hey. Today we're going to be making a gravity-powered boat. Ta-da! It's pretty easy to make. You just put water in the top here. Gravity of the water pushes it out the straw, and the boat goes forward. And it's super easy to make. You only need 4 things.
A piece of styrofoam, a plastic cup, craft stick, and a straw. And the tools you'll need: a pen, a craft knife, and the help of an adult, and science glue.
Which is the same as regular glue, except I only use this glue for science. You take your styrofoam and you cut it into a boat shape. That requires the knife and the help of the adult. Then take your cup and draw the circle that your cup will sit in. And then you want to put 2 slashes with your craft knife in there. Again, get the help of an adult if you need it. And then start carving out the styrofoam with your finger and make a nice little indent just like this for your cup to fit in. See? And then it fits in nice and snug. So then what you want to do is you want to make a hole in the cup. You can use a pencil. The hole has to be just big enough for the straw to fit in. First, you want to take the straw and dig up in this direction so that it will be a nice angle for the water to come out, and then you want to get the straw back up into the cup like that, and then glue it so that it is not going to leak any water. And then in the final step, and this is your choice, you don't have to do this, but you can use your craft stick and you can make a rudder, or if you want, you can make a whole keel, which goes just like that, and it is right in the middle of the boat, and this helps the boat go straight, because sometimes the straw goes off to the side one way or the other. Okay, water-powered boat. Actually, it's a water and gravity-powered boat. You see, what you do is you fill up the cup with water, and the gravity of the water in the cup pushes it out the straw, and the boat goes forward. And this is what it looks like in the water. You fill up the cup, and the gravity pushes the water out that way. The buoyancy of the boat keeps it afloat, and good old Newton's third law, for every action, there's an equal and opposite reaction. The water going out the straw this way pushes the boat that way, and it works pretty well. Whoa, if it's going straight. That's why we have the keel. Okay, so gravity-powered boat. Time to max it out. But first, I need an expert to help me. Oh, of course, Michaela from the Ontario Science Center. Perfect. All right, and let's go. No! I stopped myself! I didn't get wet! Now I'm just gonna get it. No! Oh. Hey, Michaela! From the Ontario Science Center, how you doing?
Good, how are you?
That was the best portal malfunction ever! Glad you're here, because I need your help maxing out this. The water gravity boat. It's pretty awesome, and what you do is you put the water in the boat, and then it does this, and it propels itself along. So, we're gonna max it out and make it super awesome.
So what do you want to do that?
Oh man, well what if we just think about making everything bigger?
Okay.
Right? Like first we're gonna need a bigger container.
Okay, well that's a good idea. Tell you what, I got my waterproof portal ordering device. So I'll order some sort of a bin.
Yeah,
Like a big
yeah.
plastic bin. Okay, hold on.
That'd be cool.
Hold on. Here it comes. Oh, there it is. Okay, so a big plastic bin.
Yeah, and then, you see this straw here? What if we had something like that, except bigger,
Like a pipe of some sort?
yeah, like a big pipe.
One pipe coming up.
I need to get myself one of those.
Yeah, but it doesn't always work, so. Oh, here it is.
Wow.
So, bin is the cup,
Yeah,
pipe is the straw.
yeah.
So now all we need is the boat.
Yeah, the platform itself. I think we need something that's gonna be really stable because we're gonna have a lot of weight this time.
How about like a surfboard or one of those stand-up paddle boards?
Yeah, that's a good idea.
Yeah, okay, check this out. Uh-oh,
Oh no,
water stopping.
that doesn't look good.
I think it might have gotten stuck.
Oh.
We'll have to go get it. Because the water is still running and that might overflow,
Man, it's
so.
stuck somewhere.
Buoyancy is the tendency for things to float. Things like this balloon or this ball in water. But it doesn't float on its own. The helium is less dense than the air molecules around it, and they fall past the balloon and push it up. The ball is less dense than the water around it, so the water molecules flow around the ball and push it up. This happens because water is a fluid. The particles flow around each other. This works because air is a fluid, and I know what you're thinking. You're thinking, Phil, air isn't a fluid, but it is. Usually we think of fluid as meaning a liquid, but in this case, fluid means anything where the particles can flow around each other, and that includes air. But you know what? It's hard to see the particles in water. Same thing with air. I can say it, but it's really hard to see it. Now this is sand, and it behaves like a fluid too. Well, sort of. Check it out. Look, it's made of a whole bunch of very fine particles, and it takes the shape of its container. But watch this. I put a ball in the sand, and it doesn't float. Now, the ball is less dense than the sand, but it doesn't float because the particles of sand have a little bit too much friction right now. But watch as we move them around and reduce the friction by adding some air. Now, this sand is behaving like a fluid, and the ball floats. Let's see what else floats on sand. How about this pumpkin? Yep, that floats. How about this block of wood? Yep, that floats too. How about this styrofoam ball? Yeah, that definitely floats. Look at that. The sand is a fluid right now because all of the little particles of sand are moving around. But watch this. If I turn off the air, everything freezes in place. Nothing floats anymore because the sand is no longer behaving like a fluid. So there you go, buoyancy. It all depends on the density of the thing and the fluid it's surrounded by. Huh? Science.
Michaela and I are maxing out our gravity-powered boat. We had a bunch of maxed out materials. We just needed to get our surfboard.
So we got our giant bin,
We got a giant tube. Water's gonna come out of this end.
and we've got a valve here, which means we can fill the bucket, and then we can turn on the valve and see what happens. So, whoa.
Hey.
Okay, you ready?
Yeah,
Now we're
here
gonna turn
we
on the
go.
valve, and that means now the water is flowing through.
Ooh,
Hey, it's working.
not bad.
Right on. Whoa, look at that. This thing is really working.
Yeah, it's taking off now.
So, okay, this is good. It's going about walking speed. Now that it's working, how do we max it out?
Our fuel here is the water, so
Yeah.
what if we just had even more water?
And it doesn't last long, does it?
Yeah.
Maxing out our boat even more is easy. A bigger bin for more water, and a wider pipe to move more water for more thrust.
Okay, so a bigger bin
Yeah.
is a lot harder to fill because it's hard to get to the top of it.
Well, you're working against gravity, so it's gonna work for us.
I can really appreciate the amount of water that we're putting into this. That's 4 buckets full.
Wow.
This is 5 buckets.
We open up the valve and it starts to go.
Yeah,
Working.
it is working. Look at all
Wow.
the awesome
Check
bubbles.
that
Okay,
That works really well.
it really, yeah, it's definitely
Wow.
faster than the other one. I think it's the larger pipe, and we need more water because it doesn't last very long.
Check it out. It looks like it's going even faster now that we've lost a bit of the water.
Less weight.
Yeah.
This is working great, so now how do we make it even better?
Okay, well, the only force working with us right now is gravity, right? Of
Right.
the water coming out. What if we add in an extra force?
And we could squish the water down to go out faster. Okay, watery high five. Okay, we gotta get it's way over here. Come on, we gotta get it. I want to move the water from this container to this container. Now, I could just pour it, but what if it's too heavy? It's too heavy! Help me, science! Well, science to the rescue with this! A clear plastic tube! Ooh, science-y. Okay, watch this. I'm gonna make a siphon, and it's pretty complicated, so follow along. Are you ready? I stick one end in here, and one end in here! Whoa! Yeah, I know, it's not working yet, but that's because we haven't added the science. First, we need to add a little bit of suction and suck the water through the hose like a straw. It has to go over the highest point. Watch this. And there we go. Look, the water is going up. I can even make the water go up even more, and it still works. But why does the water go up? Water doesn't like to go up, right? Well, the reason why is because there's more water going down than there is going up. So that creates suction on this end, and the gravity of this water pulls that water up. So gravity is doing all the work for us. And that is a siphon. Huh? So now let's max it out. This is the same container of water, but now it's colored slightly blue so you can see it go all the way up through this hose. The only really hard part about this is sucking the water all the way up to there. Okay, here we go. I got it working. Now, the reason why it's working is because there's just a bit more water on this side of the tube than there is on this side of the tube.
With a siphon, it doesn't matter how far you go up, as long as the water on one side is lower than the other.
Science. You know about helium balloons, right? Helium is a harmless gas that is less dense than air, which is why helium floats.
If I was to breathe some helium, my voice sounds higher because helium is less dense than normal air, so my vocal cords vibrate faster. Ah!
But have you ever wondered, is there a gas that's more dense than air? There is.
It's called sulfur hexafluoride, and it's much more dense than air. So if I was to breathe some, my vocal cords would vibrate slower, making my voice lower. Ha 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 ha!
This container is full of sulfur hexafluoride. Ooh, I know, it's invisible, you can't see anything. But watch as I blow some bubbles. The bubbles are floating on top of that layer of sulfur hexafluoride.
The bubbles float because they're full of regular air, which is less dense than the sulfur hexafluoride.
In fact, a balloon will float on this as well. The balloon floats lower because the weight of the latex also drags it down a bit. But the bubbles and the balloons are floating on a sea of sulfur hexafluoride. And it is like a sea because it's a fluid just like water, but it's more dense than regular air.
Science! It's awesome!
Michaela and I are maxing out our gravity-powered boat. It was already working well, but now our idea is to try squishing out the water so it gives the boat more thrust. We just had to come up with a brilliant idea how to do that.
Garbage bag! Garbage bag! Yeah, garbage bag! Okay, maybe we should explain the garbage bag. Okay, so the garbage bag is attached to the pipe at the back end. There's a hole in the garbage bag. Well, we fill the garbage bag with water. Then we tie the garbage bag tight. Tie the knot so the air doesn't get it. Now that we've got that, we use bowling balls! And we put the bowling balls on top of the garbage bag, and this will, whoa, squish the water out.
Really is pushing on that bag.
Okay, ready? Okay, let's see.
Hey, it's moving.
Our bowling balls were squishing the water out, but the boat didn't seem to be moving much faster.
I think the bowling balls made the whole thing too heavy.
What if we raise the bin up?
If it's higher up, then there would be more force due to gravity.
Yeah, so we have the bin on like stilts or something,
Oh my God.
and then it has to fall further, and then maybe the water's going faster.
I love that idea.
Okay, good.
Yeah, let's try it.
So what we need to do is get
Wait,
this.
no.
Oh, I thought this is the shallow
No,
pool.
yeah, no, that's
no,
over
that one's
there.
that's that
yeah,
one.
not here.
Max Historica.
Long, long ago, in the time of ancient Greece, there lived a genius named Archimedes. One day he was in the tub and he noticed something.
Oh, hello. Look at that. When I get into the tub, the water level goes up, and when I get out of the tub, the water level goes down. Ha ha! Eureka!
I, don't get it.
Well, I can calculate how much volume something takes up by how much water it displaces.
Yep, still not with you.
Now, I'll give you an example. How much water would be displaced, pushed aside, if I put this ball in the water?
It's light, so not much.
Ah, it doesn't matter how heavy it is. It only matters how much space it takes up. Watch. Ha! You see? The same volume, huh?
I think I see.
How much water will be displaced when I put this bowling ball in?
More because it's heavier.
Ah, nope. It doesn't matter how heavy it is. It only matters how much space it takes up. Watch.
Oh.
You see? A simple and easy way to measure something's volume.
Archimedes, one of the greatest and cleanest scientists in history. Join us next time for more Max Historica. The metric system in 60 seconds.
The metric system is a way of measuring things. Water boils at 100 degrees Celsius, a kilometer is 1,000 meters, but few people realize just how interconnected the metric system is. First of all, it breaks down to a base 10 system. Everything is 10, 100, or 1,000 of everything else, and it's all based on water. This is exactly 1 liter of water. It weighs exactly 1 kilogram. It fits into a cube 10 centimeters on each side. It boils at 100 degrees Celsius and freezes at 0. And this happy little fellow is 1 milliliter. It fits into a cube 1 centimeter on every side. It weighs exactly 1 gram, and the amount of energy required to raise this 1 degree Celsius is 1 calorie. The metric system, everything interconnected and all based on water. Ha! Oh. Uh-oh.
Michaela and I are experimenting on our maxed out gravity-powered boat. Trying to squish the water out with bowling balls added too much weight for it to make much of a difference. So now we've raised our tote higher up, which means the water will have farther to fall and be going faster when it comes out.
And I got a totally awesome name for our boat.
Tell me, what's up?
Totes McBoats.
That's a totally awesome name!
Totes McBoats? Yes! Okay, so are we ready to fire up Totes McBoats?
That's right, yep.
Okay, I'm gonna turn on the valve. Okay, ready? And let go. Totes McBoats!
What we hadn't considered is that much weight that high up would be tippy.
Totes McBoats no longer afloat.
We needed a way to solve the tipping problem first.
You know what we need to do?
What?
We need to build an outrigger.
All right, so check it out. This time we have an outrigger, which means our boat's gonna be a whole lot more stable. It's not gonna fall that way because this thing is floating. And it's not gonna fall this way because it has a lot of mass as well. I think we're almost ready, eh, Phil?
Yeah. Okay, are you ready?
Ready?
Okay, let's do it. Turn on the valve.
Here we go.
Go, Totes McBoats! Oh, yeah! Yes! Yes! Totes McBoats! Oh, the outrigger's pulling it to the side. Oh! In this way. Yes! It goes really fast.
Our gravity-powered water boat worked great. The water ran down from high up, giving it more speed due to gravity, but no more mass than before. And our outrigger kept the whole thing from tipping over. Totes McBoats was a success.
Thank you very much, Science Max Experiments at Large, gravity-powered boat, otherwise known as Totes Boats! Totes, come back, Totes! Come back! Greetings, Science Maximites. Today we're using fizzy drinks in our experiments. And a fizzy drink is just water with bubbles of carbon dioxide gas dissolved in it. So I thought since we exhale carbon dioxide, I could make a fizzy drink by just blowing bubbles in this water. Doesn't seem to be working though, does it? I don't see any bubbles, do you? No. Water does absorb carbon dioxide gas, but I don't have a fizzy drink. Weird. Time to check the book of science. Oh, in order to make bubbles, you have to have pressure. So... This is an air compressor. It takes air and compresses it, puts it under pressure. So... The container needs to be pressurized. Okay. When you get a container of a fizzy drink, the carbon dioxide gas is put in there under pressure, and it stays in there under pressure until you release it. That's the sound of the pressure being released. And when it is released, the carbon dioxide gas starts to expand. And when it expands, it creates bubbles. And that's what makes your fizzy drink. This process takes a while to run out, but eventually it will become flat. No more bubbles. But what if there was a way to release all of that carbonation all in one go? Well, there is. And for this experiment, all you need is your favorite brand of fizzy drink, Science Max brand Diet Science Cola. 100% science, 0 calories. And your favorite candy, like these Science Experiments. All the minty flavor that comes from pure science. So, all you need to do is open this up, take one of these, and put it in here with an adult's permission because it can get kind of messy. Whoa! What's going on here is all of the carbonation that was in the bottle is now being released much more rapidly than it would have been before. Now, why does this happen? Well, if you look at a carbonated beverage, you'll see that the bubbles don't come from everywhere. They come from the inside of the glass, or in this case, a lot are coming from the straw. And that's because the carbon dioxide bubbles like to find a little imperfection, something to hold on to in order to expand and bubble out. And a candy, such as this, has a ton of little tiny microscopic imperfections. So when you drop it in, there's a lot more places for the bubbles to attach, and that makes the carbonation happen a lot quicker. But remember, this is not a chemical reaction. It all has to do with carbonation. So that's what we're gonna be looking at today. Air pressure, more pressure, less pressure, and of course, we're gonna be maxing out this experiment. All right, I just need an expert to help me max this out. Let's see, oh, Cynthia from the Ontario Science Center. She'd be perfect for this. All right, good. Okay, come on, let's go. And, yep, that's good. Oh, hey, Cynthia.
Hey, Phil, how's it
Cynthia
going?
from the Ontario Science Center, you're gonna help me max out the Science Experiments and Diet Science Cola experiment. I think we need a better name for this.
Okay, well, we have the mints that have tiny little pores called nucleation sites on them. The gas inside the cola is gonna go through these nucleation sites, create a giant fountain. So why don't we call it a nucleation fountain?
Ooh, nucleation fountain, I like that. It's accurate and it sounds awesome.
There we go.
Okay, so we wanna max it out. So how many should we put in?
Let's say 5 more nucleation sites.
More reaction. Ah.
I tried adding more mints, but one at a time didn't work.
It doesn't,
No.
it's not, the bubbles are pushing it back out again. There we go, there we go. And then, yeah, I think if we put them all in at the same time, it would work better.
So we came up with a delivery mechanism to get all the mints in at the same time. A tube with a magnet holding the mints up, which we screw onto the top of the bottle. Pull the outside magnet to release, and...
Oh, nice.
Yeah.
Oh,
That's a good fountain.
That is
a good nucleation fountain.
Nucleation fountain worked very well.
There we go.
Cynthia and I decided to try some other ideas to max it out even more. We decided to do some
Experimentation.
Experimentation.
Oh, that's a good one. Yep.
and see if Diet Cola was the best carbonated drink to use. We tried 4 different kinds: Diet Cola, regular cola, lemon lime soda, and club soda.
Really just
It's just carbonated water.
carbonated water.
3, 2, 1, go. Science Cola. But I think that it was close.
I think it was the release.
Let's watch the replay.
Okay.
Yep, Diet Science Cola went the highest.
So the next step is
Maybe if we want to max the size of the fountain, we have to make a narrower stream.
so a smaller aperture opening will be higher pressure
That's what I'm thinking.
because it'll be forced at a smaller opening. What else can we do?
We can launch it.
We could launch. Oh, you mean like sideways?
Yeah.
Yeah, I love that idea. So we'll put it on wheels. We'll put it on wheels.
Okay.
And then we'll launch it sideways.
Okay.
We got a lot of things to do. Okay, let's get.
We need time. Let's do it.
Get to it. Okay, we'll go to
Okay.
the lab. I'll get a mop. Nothing like a fizzy glass of water. And now there are ways for you to carbonate water at home with something like this, the Science Max Carbonation Station. You have a bottle of compressed carbon dioxide gas that's hooked up.
You take a bottle of tap water, attach it, and carbonate it.
Voila! Carbonated water. But this is Science Max. Why just carbonate water? Let's carbonate everything! Let's carbonate pickle juice. It's actually amazing. Milk! It's like milk meets water, kind of very odd. Chocolate milk? Oh no, that's way better. Carbonated mustard. Carbonated tomato juice? Carbonated hot sauce. No, wait, carbonated. That was the hot sauce. No. Carbonated clam chowder. Oh, there you go. Carbonation. Not just for water anymore. It is definitely not for clam chowder. No, that's just a big bowl of no. Never again.
Cynthia and I are maxing out a nucleation fountain.
Yeah.
Oh,
That's a good fountain.
We're changing our design a bit to see if a smaller hole in the bottle cap will make for a higher pressure fountain, which will make it more maxed out.
We have this large hole. We've got a medium-sized hole.
We have a very small hole
So we're gonna see large, medium, or small, which one is the best.
to max out our fountain.
Exactly.
But the problem is that our old delivery mechanism won't work if we keep the cap on. So we needed to come up with a new delivery system. So we drilled holes in the mints and put them underneath the cap on a pipe cleaner. They hang at the top of the bottle until we pull the pipe cleaner, and then they fall in.
All right, are you ready?
Oh, I'm so excited. Which one do you predict will be the best? This will have a larger geyser.
I
These
think
ones
this will
be small.
look cooler
Yeah.
because it'll be big, but this one?
The smallest hole, I think, will go the highest.
Yeah. Ready?
Three,
2,
two,
1. Oh, definitely the biggest.
There. Whoa, careful, careful, careful. Whoa.
This one is almost like a spray.
It's not like a mist.
Yeah,
it's a
a
mist
mist.
of cola. They all kind of worked a little differently. The interesting thing is this one lasts the longest.
Oh.
There we go. So, this was cool, but not the best.
This one's still going.
It's still
It's
going.
not over yet.
You gotta give it points for still going.
I think this fountain looked the best, though.
This one was pretty good. So, a small aperture, but maybe not the smallest aperture, would be the best. So because of the force coming out of here, I think that we could probably do something like putting it on wheels.
And shooting it like a rocket?
Yeah, let's see.
On wheels?
Or like a car.
Oh.
Yeah, we'll make a a nucleation fountain car. The Nucleation 1! Boo!
It's our race car.
It's our race car. It's got fancy wheels that spin really well.
And we decided to go with the medium aperture. So it's fairly big, but not too small.
Yeah, all we need to do is unscrew that, put that in there, and then pull it out.
3, 2, 1. Oh, good, good, good. Let it go. Oh, that's not so bad.
Oh, yeah!
Missed the finish line.
Past the thing! Turn it around, turn it around!
Did we make it get to the finish line?
There, it's
No.
spinning out.
Oh, wow.
Go, go!
It worked pretty well, but there's always more ways to max it out.
What if we just got like a giant container? Like, because we're using small containers, right? What if we just
So
got a
you
really
want to
large
carbonate
container?
a very large container.
Well, we'd have to figure out some way to, well, come on, let's go figure it out.
Okay, let's do it.
This is an egg. It's been hard-boiled and peeled, so there's no shell on it. This is a flask, and this is hot water. I pour the hot water into the flask, which means the air inside the flask starts to heat up. And when it heats up, it expands, and some escapes through the top of the bottle. I pour the water out, and then I cap the flask with the egg. Now this expanded air is starting to cool again, which means it's lower pressure, which means the higher pressure on the outside of the flask pushes the egg in. Ha-ha! Fun! And then, to get the egg out, I can reverse it. If I blow into the flask, I can increase the pressure inside. Science! And now let's max it out. Max out container! Okay, pour out the water. Oh, careful, careful. And now, I put this water balloon on the top, and we'll just see what happens.
The hot, expanded air inside the container is cooling and reducing in pressure, which means the higher pressure outside the container
It's happening!
pushes the balloon in.
It's happening! Oh. Success! Maxed out!
Did you know that we live on the bottom of an ocean of air? It's called the atmosphere. And compared to the Earth, it's really thin. I mean, it's about as thin as this. Huh? Huh? Look at that. Not very thick at all. But it's a good thing the atmosphere is around, and not just for breathing. Though I am a fan of breathing. What do we want? Breathing! When do we want it? All the time. But did you know the atmosphere has different layers? It's true. I will walk you through them. No, I mean, come on, you gotta come with me. I'm walking over to walk you through them. Okay, the troposphere. This is the layer where we are all existing right now, where all of our weather happens. There's a lot of air molecules in this layer. Think of these balloons as air molecules. There's a lot of air in this layer. Yay, air! Next layer, the stratosphere. There's less air molecules in this layer, and it's where jets fly. Next layer, the mesosphere. There's even fewer air molecules in here, and it's where meteors burn up and turn into shooting stars. Fire, 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 fire! Whoa. The thermosphere. Not many air molecules left up here, and this is where the northern lights, the auroras, happen. Woo! Northern lights. And finally, the exosphere. This is as high as the atmosphere goes. This is where satellites orbit, and if you see any air molecules up here, they're just passing through.
Hello.
And after that, nothing but the vacuum of space.
Ooh, the vacuum of space!
Of course, you know it's not that kind of vacuum, right?
Right, vacuum just means no air. There you go, the atmosphere. The only thing separating us from the vacuum. vacuum of space! Roberta, your space vacuum got broken. I don't know how.
Cynthia and I are maxing out the nucleation fountain.
This one is almost like a spray.
It's like a mist.
Yeah,
it's a mist of cola.
Just to experiment, we tried using a giant bottle and pouring the Diet Cola in.
I'm a little concerned about the science.
But it didn't work.
Well, that's not very exciting.
Okay, so that didn't work at all.
No,
This is not a chemical reaction.
it's a physical change.
So it's the carbonation that matters.
Exactly.
When we poured the cola into the bottle, we lost almost all the carbonation.
How are we gonna max it out?
That's the question. So if we can't make a larger container,
More bottles?
we just have more bottles. So we'll just get a
Exactly.
lot of them and we'll set them off in a sequence or something.
Okay, let's do a pattern or something. We'll max out the
I know what we
fountain.
should do. You know, we should be sort of like a cascade and we'll get a lazy Susan or This is a vacuum chamber. It's an airtight container, and I put a hose on it, and the hose is attached to a pump. Now, the pump takes the air out of the chamber, creating a vacuum. So, let's have some fun putting things in a vacuum chamber. Marshmallows in a vacuum chamber.
The marshmallows grow larger,
Whoa!
then shrink much smaller when returned to normal pressure. Why? Well, take a look at what happens with this balloon. The vacuum takes the air and the pressure out of the container, which was pushing against the sides of the balloon. Without that outside pressure, the air molecules inside the balloon can expand. So let's max it out with,
Maxed out marshmallow.
just like the balloon, the marshmallows expand. But unlike the balloon, the air in the marshmallows escapes. So they shrink when the pressure is added back in.
They're almost the size of regular marshmallows.
It's the air inside a marshmallow that makes it fluffy.
It's not very fluffy.
The same expanding process happens with marshmallow cookies,
The marshmallow has completely deflated and it's all kind of hollow inside.
the frosting on a cake,
More cake! No, no! Oh! Look at this giant birthday cake. I can't wait to eat it. No! No! Why birthday cake?
and even shaving cream.
No! Shaving slime.
Cynthia and I have done a whole bunch of different experiments
Experiments.
to find out how to max out the nucleation fountain.
So we'll just get a lot of them and we'll set them off in a sequence or something.
Okay, let's do a pattern or something.
Now we have a bunch of bottles and we're ready to try the maxed out version.
We've got our release mechanism.
With our medium aperture.
Yep, and we're gonna put the mints in all of the bottles and then we're gonna release them in a very coordinated,
Pattern.
rehearsed pattern.
Very rehearsed.
We've rehearsed it a couple times. We'll see how it goes. And we've got this lazy Susan, which will spin around and we'll see how it goes. And 3,
2, 1. 1,
2,
3,
4,
5,
6,
7. Surprise! 1, 2. Oh, go, 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 go. 3, 4. We did it!
Whoa!
It's raining Diet Science Cola. We maxed it out!
Maxed out! Nucleation fountain. That is as good as it's gonna get.
So let's recap. Our nucleation fountain is all about releasing the carbonation in our Diet Cola faster than normal. This happens because there's lots of tiny bumps on the mints for the carbon dioxide to grab onto and make bubbles.
High fives. There you go. Science Max Experiments at Large Nucleation Fountain. Excellent job. Now all we need to do is clean it up.
Clean up, and I think I need a shower with water.
Yeah, I think I need at least the towel.
Yeah,
Okay,
but it's supposed to volumize your hair.
Is it good for
I
your
think
hair?
so.
I
Yeah,
hope so.
better than
'cause-
honey.
Greetings, Science Maximites. My name is Phil, and this is Science Max Experiments at Large. Whoa. Oh, I better spin the other way. Today, we're gonna be taking a closer look at spinning. Well, all things spinning. Spinning, rolling, rotation in all its forms. And, when things spin, they're subject to a whole bunch of different forces, and some are strong enough to even counteract gravity. So let's get spinning! Oh. Okay, let's get spinning! We are going to make a gyroscopic whirligig, and it spins, and I don't, which is a good thing. Watch this. You pull the string, and it spins, and it stands on its end.
Why does it stand on its end when it spins? Because of angular momentum, which we'll get to later.
And here's how you can make one of your own.
You will need some craft sticks, string, a small zip tie, a shish kebab skewer, spacers like these wood blocks, and finally some round discs, which you can cut out of plastic or find from parts of broken toys. Now, if you want to research this yourself, look up gyroscopic whirligig.
Get 2 craft sticks and glue them to your wooden blocks just like this, and then do it again.
Space them apart and glue them to crosswise craft sticks, and this will be your launcher.
You put your hand in the small end, and the longer end here is where you put your gyroscopic whirligig. Now let's make that. What you want to do is you want to take a shish kebab skewer or whatever fits the diameter hole of the round things that you're using. I like to use little plastic discs from, these are from remote control mechanisms, but you can use anything you want.
I found that this launcher works best with 4 discs of the same size.
Just like that.
Space them out evenly, glue them down, and cut the skewer even on both sides. Then add your zip tie. Put it right in the middle, tighten it up, and cut off the dangling end. This zip tie just gives you somewhere for the string to hold on when you wind it up. Now for your pull handle. Glue 2 craft sticks and 2 wooden blocks, then 2 more craft sticks on the sides. Then tie a string to the middle, wrap that string around the middle of the whirligig, and
Aha! You have a gyroscopic whirligig, a pull handle, a rope, and your launcher. Now remember, you put your hand in like this, and you fit your gyroscopic whirligig in just like that, and you pull towards you, and it spins! Oh, and that's what we're gonna be doing today, Science Maximites. We're gonna max out a spinning rig, something like this. It's gonna spin bigger, faster, more weight. It's gonna be totally maxed out. So come on. But first I need an expert to help me out. So let's see here. Wait a minute. Aha! Perfect. Come on, this is gonna be great. Okay, this is it. Hey, Silena from the Ontario Science Center. I'm really glad you're here. You're gonna help me max out the gyroscopic whirligig.
The what?
Oh, the gyroscopic whirligig. Here, I'll show you. It's this, and it spins, and what works on
Phil, where are your shoes?
I think these are my shoes. They must have changed into flippers in the portal. Weird.
Want to change them?
Yeah, I'll be fine. Anyway, like I was saying, the gyroscopic whirligig is really good. Let's do it here so that I don't have to walk as far.
Can I see it?
Yeah, here it is. Ready? You spin it up, and it spins, and it goes for a while, right?
Because you made it out of 4 discs, it probably spins better because there's more mass.
Oh yeah, because you know what? I actually have an old one. Yeah, I got an old one here with 1 disc, and it does not spin as long as the 4-disc one.
Could we test the 1-disc one out and compare it to the 4-disc one?
You bet, because you know what that is?
Science.
Yeah, that's science. Okay, let's try it. Ready? Whoa.
Huh, look at that. The 4-disc one spins better longer than the 1-disc one because the 4-disc one has more
mass, therefore more inertia. So when we max it out, we should get something with a lot of mass.
Yeah, more mass.
Wait, I have something right. Well, Can you give me a hand?
Careful, Phil. I don't want you to fall.
Yeah, well, I don't want to fall either. It's hard to walk in these.
I can imagine. That's why I asked you if you wanted to change your
Nah, we're
shoes.
fine. I'm fine. Okay, check it out. This is what I was going to. Okay, this is what we can make it into our maxed out spinning gyroscopic. Why not?
It's just, look at how big the hole is.
Oh, yeah, because we're going to need something to be the axis, huh?
Yeah, we need like a tree to fill that. I don't
Yeah,
think
you're
that's
right.
gonna work.
Too big. Is there anything else wrong with it?
It's also kind of light. It's not that heavy.
More mass, better.
More mass.
Okay, tell you what. Oh, I know. Hold on. I know. Whoa.
Oh, that looks perfect.
Yeah, and then we got this pole.
To go through the center?
We'll go through the center like that.
Awesome.
And then we'll just weld it together, and there you go.
This will be great.
Yeah, high five.
Phil.
Okay, no, wait, sorry, yeah, you got the thing.
High five.
Well, now I got the thing.
Yeah.
All right, I'll get new shoes, and we'll work on our high
Okay.
five. Now it's time for one of my favorite scientific terms, the Magnus effect.
I am Magnus, and behold my effect.
No, the Magnus effect has to do with things that are spinning. Things like these cups. And here's a great little Magnus effect flyer you can make at home. It's super easy. Get 2 styrofoam cups and tape them together at the bottoms using science tape. Then get some elastic bands and make a long one by tying them together. Take your elastic and you wrap it around the cup like this. Then hold the elastic on the bottom, remember, like that, and then let them go. They fly up and out.
The reason why it goes up and stays in the air is because it's spinning, creating moving air over the top. Moving air has lower pressure, which means it's pushed up by the higher pressure underneath.
And that is called the... It's coming. Oh, come on.
Now, the Magnus effect.
Yes. So, let's max it out.
Magnus it out. See how much better that sounds?
No. Max it out. Check it out. Magnus Flyer 2.0 stand elastic slingshot. Wrap it around.
Remember, for the Magnus effect to work, your cups need to be spinning this way, the front side rotating up.
Oh, and there you have it, the Magnus effect.
I, Magnus, am now taking over the show. It is now Science Magnus. That is my effect, slightly improving the name of science TV shows. Science Magnus.
Silita and I are maxing out our spinning top. Based on our small version, we decided to make one with as much mass as possible. So we got a 20-kilogram weight and welded it to a metal shaft. Will this work the same way? Well, let's look at the science. Why does a top spin? Well, let's start with Newton's first law, which is an object at rest tends to stay at rest, an object in motion tends to stay in motion. But the in motion has another part. That object also wants to go in a straight line. If you think of a bowling ball rolling along, it would need another force to act upon it to make it change direction. We say that a moving object has momentum. Now, a top doesn't go in a straight line, it spins around, but it still has momentum. It's an object in motion, and even though it's spinning, it still does want to go in a straight line. It's just that that straight line is here. We call this angular momentum. To make a top move this way, or that way, would take an outside force, so it stays upright as long as it has enough momentum. But when it slows down, there's less momentum and it becomes harder to resist external forces, like gravity, which will eventually want to make it topple. Our top has a lot of mass, which means it'll have a lot of angular momentum when it gets spinning. It's just a matter of getting it spinning fast enough.
So should we spin it?
Yeah, let's spin it. Let's see if we can get it to work. Hey, okay.
Spin.
We're gonna let go. In 3.
Wait. I can't get it.
1.
Wait.
Okay.
Okay, not fast enough.
We need something to help us get it spinning faster. Maybe a rope?
A rope, yeah.
Wrap a rope
That
around
was
it,
my
like the-
idea too, a rope, because the small one uses a rope.
Yes.
Okay.
Okay, I'll go grab a rope.
So, wrapping the rope up.
I'll let you wrap the rope
Okay.
up. I'll get my holder back on top.
Spin it counterclockwise.
We attach the rope and wind it up.
You wanna make it super clean. This is some of the best coiled rope I've ever seen. I'm gonna pull the rope. You're gonna hold on to it, but I can't pull really hard because you won't be able to hold it up. Because we don't have to pull hard, we just have to get it going fast.
Yes.
Silita keeps her hand on the block at the top, and I pull.
Ready?
Wait a minute, we'll get all the way. Oh. Whoa!
Spinning a lot better than I thought it would. It's still spinning, but it's wobbling.
Oh, careful.
Oh, there it goes.
It works, but just barely.
It might spin better, it might spin straighter.
Yeah.
If we had it spinning, something help us spin it faster.
Yes, faster with more power.
With more power.
This is a string. You can pull a string, but you can't push a string. Well, you can. You can push a string. You really can. Okay, quit it. Quit it. This little contraption works sort of like a baseball pitching machine, but in miniature. See, there are two motors here, and the wheels spin together to shoot things out this way. Things like this craft stick. Watch this. Whoa! Let's watch that again. Whoa! But now, watch as I put a large loop of string through. What? Pushing string. How does this happen? Hello?
I don't suppose it's the Magnus effect?
No, it's not the Magnus effect.
No, it's all right. I'll be in my lair if you need me.
Okay, right. Bye. Right. Where was I?
I believe you were at, the reason why this works is...
Right. Pushing string. How does this happen? It's all because of inertia. Check it out. The wheels are pushing the string through fast. It's got some weight and it's got some speed, which means it has some inertia. So when it goes this way, it wants to keep going this way. But it goes all the way to the end, and then, because it's a loop, gets sucked back in this way, which means all of this inertia, you can sort of overcome gravity. Pushing string. Science.
Silita and I need to get our maxed out top spinning faster. We tried a rope, but now we're trying a drill. We get a wheel on our drill and use it on the outside of the weight to get it spinning up.
A little faster.
Oh, it's wobbling now.
A little more.
Push me.
And release.
It's kind of cool that it wobbles that much and it doesn't hit the ground.
It worked better, but there's always a way to max it out even more.
You know what we need, Silita?
What do we need, Phil?
A maxed out drill. Put it right on the top here and get it spinning very, very fast. Super maxed out gyroscope
Okay.
whirly gig.
Gig.
Is it just the top now?
I don't know. Do you
We
want to
could
be
call it
calling
a gyroscope.
gyroscopic
Well,
whirly
it's sort of a toppy, kind of gyroscopy. This is a bike tire. It's pretty light, but I still can't hold it from the end of the pole like this with one hand. Nope, nope. But I can if I get it spinning fast enough. I just use this drill, and then I get... Okay, so this is gonna be awfully hard to do with one person. Oh, this is the perfect opportunity to use the Trevor button. Trevor button. Hey, Trevor from the Science Max build team. What are you doing?
Maxing this out.
Oh, right on. Can you give me a hand for a second?
Sure.
Awesome. Okay, so you take this drill, and we're gonna get this wheel spinning really fast.
Okay. I don't know if it's,
No, I don't want to know.
I don't know if I remembered to...
No, it's fine. Max it out. We gotta max it out. So, because it's spinning, I can hold this heavy weight in the air.
How is this possible? Because the wheel is basically a top. The forces that prevent a top tipping, angular momentum, are still working here. This angular momentum resists a change in direction this way, which is how gravity would want it to tip. Interestingly, these same forces also keep it spinning around me in a circle.
So I can lift a heavy weight in the air just by spinning it. Awesome max out experiment, Trevor.
Yeah!
What was that?
It's my science confetti high five I just made.
You know what we should do?
What?
We should max it out. Yeah, we can make a giant one and then a whole bunch of confetti in it, and then people like jump up and do more confetti that would come out, right? And then so what would happen is there would be all this Trevor?
Silita and I have maxed out our spinning top. The trick is getting something that heavy to spin really fast. We've tried a rope and a drill, but now we have a maxed out drill.
So more power and more speed, which is perfect for spinning this massive top.
Yes, and perfect for maxing out anything.
We get it spinning and it works great. The top spins for a really long time. In fact, its mass was so large, it started drilling a hole in the concrete floor. We tried it again, but started to notice something.
The drill is smoking quite significantly.
Our drill began to overheat. Why? Good old Newton's first law. An object at rest wants to stay at rest, and an object in motion wants to stay in motion. The more mass we have in motion, the longer it will stay in motion.
This will go forever. Well, not forever,
Well, not
but
forever.
it'll go a really long time because it's got a lot of weight.
But that same mass wants to stay at rest when it's not moving. We have to overcome all that mass wanting to stay at rest to get the top spinning. And even for our maxed out drill, that was a tough job. But once it was spinning, there was only one thing to do. Max it out even more! Silita and I come up with a plan to max out the top by riding it.
You want to ride the top?
Of course I want to ride the top.
We can both ride the top. One person's gonna have to drill this, so we'll have to take turns.
Max Historica.
This is Leonardo da Vinci, one of the greatest scientific minds the world has ever seen. And this is a wheel. Da Vinci thought to himself, wouldn't it be great to design a wheel that kept spinning forever? So he got to work. Something that keeps spinning forever without stopping is called a perpetual motion machine. And it was an obsession of Da Vinci's. Why, this is great. The bottles tip the water to the outside, making one side of the wheel heavier, which will keep it spinning forever. Except it doesn't work. You see, what Da Vinci doesn't know is that science says a perpetual motion machine is impossible. But of course it wasn't for another 350 years till scientists figured that out. So we can't tell Da Vinci. What? Oh, never mind. Leonardo da Vinci, one of the greatest inventors ever. Even if not all of his inventions worked. Silita and I got our maxed out spinning top to work pretty well. The only thing left to do was to ride it. We attached a large disc and a Lazy Susan. That's a platform that spins around on ball bearings.
Lazy Susan on top,
Lazy Susan.
so that you can ride on it.
Yes, and then we wanted to add this extra bit. Now, why did we want to add this?
We need a little bit more weight on our top.
Okay, so who gets to ride it?
I feel like you should ride it.
I think you might be right.
Because I want to use
Oh,
the drill.
the super awesome maxed out drill. Okay, so let's do it. First thing I should say is do not try this at home. We are trained scientists.
Silita uses the drill to get it spinning while I hold it steady. Then I hold on to our safety line above and carefully rest my weight on the top. It works, but not for long. We take turns trying it out, but it seems we have another part of science working against us. Good old friction. Friction with the air and with the ground is what eventually slows a spinning top down. But our weight on the ball bearings of the Lazy Susan really increases the friction. More friction means the top slows down a lot faster.
Whoa!
That was pretty cool.
It was kind of terrifying, right?
Yeah.
Good old Newton's first law kept the top spinning, angular momentum kept it from falling over, and friction slowed it back down. The forces were always the same, no matter if it was a little top, a maxed out top, or a rideable one.
Yeah! Whoa. There you go, Science Max, experiments at large, giant spinning top. That's as large a spinning top as I think you.
I think in the entire world.
Let's do it again. Yeah! Greetings, Science Maximites. My name is Phil, and today we're talking about friction. Oh, it didn't slide.
Take 2.
I can't. I'm still not. Oh, I know. I got it.
Take 3.
Socks don't work any better.
Take 15. 34. Take 36.
I don't know why I thought that would work.
Take 52.
I'm Phil, and today we're talking about friction. Sorry. Okay. Whoa. Friction. We did it. We got it, everybody. How many takes was that? Oh. Well, still, we got it. Good work. As you may have already guessed, today is about friction, and here's a really easy friction experiment you can do at home. All you need is a piece of wood. You don't need the frame, and you don't have to do anything fancy to it. Just put one end up on a couch or a coffee table and make a nice ramp. Then you want something to slide down that ramp, and I like to use a piece of wood. Now check it out. Wood ramp, wood block. The friction is so much that the wood slides to there. Now what I like to do is take a little flag and mark the results. Recording the results is good science. Now here's where it gets fun. Get another surface and attach it to the wood, like carpet and wood. Let's see how far this goes. Not as good. All right, record the results. Cardboard. Ooh, nicely done, cardboard. Foam. And this wood has been waxed, like on a floor wax, which makes it nice and slippery. Let's see how that does. Ooh. And now the ultimate ice attached to wood. This is actually harder to do than I thought. All right, let's try it out. Ice! The clear winner. Not a big surprise right there. And get this, once you've done all of that, you can change the surface of the ramp. You can go to waxed wood, carpet, foam, cardboard. Well, well, yeah, you get the idea. Record all the results, compare them, and there you go. Friction ramp experiment. And that's what we're gonna be maxing out today. So come on, let's go. Check it out, I've improved the portal interface. Watch this. Yeah, and then I can scroll through experts, and oh, this is gonna be fun. And I've got my coordinates right there. Oh, that's never happened. Okay. Hey, Sarah!
Hey, good to see you again.
Good to see you too, Sarah. From Mad Science, you're gonna help me max out friction.
Yeah, friction.
What do you think of my max out friction room?
It's amazing. It's so wonderful. So how are we gonna max out friction today?
In the lab, I had a ramp, and I had stuff with different surfaces on it.
Oh, that's so cool. It's too bad you don't have it here. We could totally test that out.
I can bring it here.
Awesome.
I have a new app on my phone that talks to the portal, and let's see. That's not what I. Oh, hold on. Okay, there we go. And whoa. Well, I can do this. I just it needs an update.
Yeah.
That's what the.
There we
it
go.
is. Okay.
Perfect.
So here we go.
Amazing.
The friction ramp. It's pretty simple. You just take. I've got blocks of wood with different surfaces.
Amazing.
And then you just slide them down the ramp.
Right. So cool.
Yeah. So what if to max it out? What if this is us?
We're a block of wood?
No, I mean like we are on the block of wood, and then we can try changing the bottom. I guess a block of wood isn't the right thing to use, though.
Right, yeah. Maybe we could use like a sled.
Yeah, okay, like a snow sled. That's a great idea. Okay, so we'll tell you what. I will portal in a sled for us.
Are you sure you want to portal it in?
I'm sure. Just stand back,
Okay.
though. Okay. Ha!
Ah, there we go.
Maxed out friction slide!
right, you ready, Sarah?
Yeah, I'm ready.
Okay, here we go.
All right.
Sarah and I pushed each other around on the sled, which was fun, but it was also tiring.
It's pretty hard. This is
My turn. My turn.
All right.
Yeah! Whoa, friction! Yeah, friction! Yeah! Yeah, friction!
But we soon realized it'd be pretty hard to measure how much friction there was.
You know how hard you were pushing?
I had no idea how hard I was pushing.
A lot, but that doesn't really help in science terms. So
Exactly.
what do we do?
Well, with your first experiment, you used a ramp. Could we maybe put a ramp up in here?
In here?
In here, yeah.
I guess.
Then we can measure also how far we go so we know how much friction is being used.
Right, so we have our control, and then we have all the, just like the blocks.
Exactly, just like the block.
Okay, great. So we'll get the ramp, we'll get a bunch of wood,
Yes.
we'll get some tools.
Yeah.
The case of the missing friction! It was rough all over in the big city. My toughest case yet, and I felt like I was getting nowhere. Someone stole all the city's friction. And it was my job to find out who and get it back. But after a week, I was no closer to solving the case. It was hard to get anything done now that there was no friction. Uptown to downtown, people were sliding all over with no way to stop themselves. It was chaos. Chaos, I tell you. But if there was any detective that could solve the case, it was me. But it's like my grandma always said, it's tough to follow leads if you can't sit in your chair. Nothing stays put in a city without friction. And you never appreciate something till it's gone. The phone rang. Sure, I wanted to answer it, but it slipped through my grasp just like this case. The mayor was on the line. He wanted to know if I'd made any progress. But I felt I was going in circles.
I'm gonna have to call you back, Mr. Mayor.
Without friction, you couldn't do very much at all. It was going to be my toughest case yet.
Sounds good.
Sarah and I are maxing out a friction ramp. Step 1, make a giant ramp.
There, are we done?
Hey, I think so.
We're done. But it proved a bit hard to lift up to the second floor. Fortunately, Sarah had an idea.
Maybe we could use this crane.
We use the crane! Oh, yeah, I've got a 5-ton crane at Science Max headquarters. Good thinking, Sarah.
So we rigged it up and tried it out. The bonus was we could make the ramp any angle we wanted.
Okay, time to get my helmet, because don't go any higher than that, because I don't have my helmet. And then we will start sliding down. Friction ramp!
I got on the slide and Sarah lifted it up until I started moving. And that allowed us to record our results.
We're at 2 meters.
2 meters! Recorded! First recording done, now we switch it up.
We tried it again with Sarah on the slide to see if she slid at the same height. And she did.
Yeah.
Now we have a way to record the results. The plastic sled went down the ramp at this height. Things with more friction will mean the mark is higher, and less friction will mean the mark is lower. So then, we tried it with...
Cardboard! Cardboard! What did we get?
And it was...
A little over 2 meters.
Meaning?
Cardboard is a little bit less slippy than the plastic of the sled.
All right.
Ready for carpet sled?
Good to go.
Here we go. Oh, past 2 meters. Oh, almost 3.
Here we go.
Carpet had even more.
Oh my gosh, we're going to the side.
Whoa!
That was so cool.
That was exactly 3.
Then we tried foam.
Coming up on 2 meters. All right, coming up to 3. It won't go up any higher.
And just like the wood block, the foam didn't slide at all.
What if I do this and then I slide? Right, so, friction sled, on foam, highest friction of all of the materials. Oh, hello there. Here's a fun science experiment you can do with science and friction together. Take two books, put them on top of each other, and pull them apart. Ooh, not too much friction. But if you take the books and you interleave some of the pages, maybe 3 or 4 parts, and try it again, pull them apart, they're a little harder to pull apart. That's because the friction for more pages touching each other actually starts to add up. So, what if we were to take two books with a lot of pages and very carefully and meticulously take each page individually, one at a time, and overlay each one and go back and forth? These are two books completely shuffled together. The elastic band is actually just to hold the covers together. All right. So, now the friction between all of these pages, when I try to pull it apart, makes it pretty much impossible. Now, there's two things going on here. First of all, when you start to pull the books apart, the pages start to stick together because they squeeze together, because you're pulling and they're squeezing. And the fact that there's so many pages sticking together, the friction builds up to a degree that is actually very impressive. But don't take my word for it, let's max it out. Here is another two books, elastic just to hold the covers. This one clamped to the wall, and I'm gonna pull on this one. Science! Still don't believe me? Well, let's max it out some more. Two books, all the pages layered together, held together only by friction suspended over a giant vat of slime. Now, let's see how much faith I have in science. Friction! Yeah! Okay. Okay, oh no. Okay, now to get down. Okay, hold on. And then... Science! That was close.
Sarah and I have used our maxed out friction ramp and compared the regular sled to cardboard and foam. What's next?
We've waxed the bottom of this sled, and we're gonna try a wax sled next.
Wax sled!
All right, here we go. Right.
1 meter.
Oh boy.
1.5 meters.
Whoa!
Wax sled! Woo! The slipperiest yet, only 1.5 meters.
That's awesome. Do we have anything that's more slippery?
Yeah, we do. We have ice sled. Are you ready to try it out?
So ready to try it out.
Okay, let's do it.
All right.
And
there we go. Whoa! That was awesome.
Look how far you went.
That was so cool.
And only 1.25 meters.
Least amount of friction.
Ice wins. So, I think we should do something else to max this out, though.
Maybe bringing it up a little bit more and using something with less friction.
Wait, I have an idea. Yeah, okay, come with me. This is a climbing frog. Why does it climb? Because of science. I pull on this rope, and then I pull on that rope, and I pull on that rope, and he climbs up the ropes. And why? Well, because of friction. The secret is 2 straws.
The straws are pointed away from each other at the bottom. This allows it to climb thanks to friction. Take a closer look. When I pull on one string, it pulls straight, which makes the frog pivot. That string slips through the straw because there's not a lot of friction, but there's lots of friction on the other side because of the angle. So one side of the string goes down, which makes the other go up, which means the frog goes up with it, all thanks to friction.
So now, let's max it out. This is a super maxed out climbing frog.
Just like the small version, I have a rope going through 2 tubes. I pull on one rope and the other holds on by friction. Then I switch.
And it does work. It's just a lot harder to pull on the ropes. But it totally works. Whoa, careful. Whoa. There, and then this one, and then that one, and then that one. Yeah! A giant climbing frog! All because of friction. Here's another way to defy gravity using friction. Get a plastic water bottle and fill it with rice.
Take two.
So get a plastic water bottle and fill it with rice using a funnel. Then take a shish kebab skewer and stick it into the bottle and nothing happens. But if you tap the bottle down, the rice starts to pack in a little bit better. See how the level of rice is lower? Which means you can add more rice. Pack it down even more. And you can even use something the same diameter as the mouth of the bottle, like, say, a highlighter. And make sure all the rice is as packed in as you can get it. There. Now the rice is really packed in there. And when I stick the shish kebab skewer in, the friction between the pieces of rice and this wood is enough to lift the bottle using nothing but friction. Now, let's max it out. I filled this 20-liter water cooler jug full of rice, and it's really heavy. I wanted to see if I could lift it using nothing but friction and this dowel, which is just a round piece of wood. All right, here we go. Ah, science! I'd max it out even more, but I don't think I could lift anymore. It's okay, I can just fit.
Newton's first law in 60 seconds.
Newton's first law says an object in motion tends to stay in motion. So why don't they? See, if I was to throw this, it doesn't stay in motion, it doesn't keep going, it slows down and falls to the ground. Well, the whole law states an object in motion tends to stay in motion until an external force acts upon it. So what forces are acting upon this? Well, gravity for one, pulling it down towards the ground, and friction, specifically air friction, slowing this down and making it stop. Now, if you were to have something very light with a lot of surface area, it would really be affected by air friction. You wouldn't be able to throw it very far at all, no matter how hard you tried. So there you go. Newton's first law, an object in motion tends to stay in motion unless it's affected by an external force, such as friction, like air friction. So there you go.
Sarah and I have recorded a lot of results on our ramp by raising it till we started to slide.
Here we go.
Now we've decided to raise the ramp to the highest point and see how far we can go using some low friction things, like a wheeled cart.
I've made a double bike cart.
Wheels are great for moving. They have rolling friction,
Ready?
which is different from sliding friction.
What happened?
You went through all those boxes back there.
That was it. We went really far. Total fun. Let's try something else.
So what are we gonna do next?
Now we're gonna do the frictionless thing that we have at Science Max headquarters, a hover disc.
Oh my gosh, that's so cool. Where did you get it?
Built it, season 1.
Amazing.
As you may remember from that episode, a hover disc uses air to greatly reduce the friction with the ground.
Here we go.
So what would a hover disc do on a ramp?
Right.
Only one way to find out.
Whoa! That was amazing.
That was awesome.
So let's recap. Friction is when two surfaces rub against each other. You can have a very small amount of friction or a very large amount, depending on the materials. And using science to reduce friction results in the best sledding experiences.
Nicely done. Science Max, experiments at large. Your turn.
My turn? Yeah, let's do
Okay,
it.
so take those, and I'll get this, and then I'll give you the helmet. And then we gotta rebuilding the boxes is like the hardest part of this
Yeah.
whole situation. But Greetings, Science Maximites! My name is Phil and welcome to Science Max Experiments at Large. Today we're gonna be looking at air pressure and friction and simple machines like levers, pulleys, and gears. We're gonna look at some rotational energy, some spring tension, and gravity. We need all those things because we're building Rube Goldberg machines! Rube Goldberg machines! Rube Goldberg machines! Rube Goldberg machines! Rube Goldberg, you heard me say Rube Goldberg machine. Okay, we got that part? Okay, good. Rube Goldberg was a cartoonist who came up with the idea of having a simple task done by a machine that was extremely complicated. There are Rube Goldberg competitions all over the world, and there's only a few rules. First, a human can only touch it once by starting the whole thing off, and then the machine has to work all on its own. I know what you're thinking. You're thinking, Phil, what's the science behind a Rube Goldberg machine? Well, it's all about changing energy. Remember, you start the whole thing off with just a little push. But if you want the machine to keep going and going and going, you have to come up with clever ways to add more energy to the system so you've got more energy to keep the machine going. So check this out. A bunch of stacked dominoes, which will start a chain reaction that leads to this mouse trap, which has all of its energy stored in the spring tension, which will release the ball. Boing! Check this one out. It's a bunch of pulleys, and there's a rope that goes up and down and up, attached to this lever where there's a ball, and there's a big, heavy weight here. And when the weight gets knocked off the table, the ball falls into the hole and then goes down the tube, and so on. Check this one out. Here's a great way to change the direction of something. Say the ball falls on this lever. Well, it's weighted on this end, but then the weight falls off, and the ball goes this way. And, the portal turned on. I gotta pick an expert. Okay. Hold on a second. 10 seconds before the portal resets. Sonia from the Ontario Science Center. Perfect. And there we go. Tons of time. 3, 2, 1.
Oh.
Sonia.
Hey.
I portaled in 3 blocks away. I had to run here.
Okay. You're here now?
Yeah, I didn't put the coordinates in when I left. Anyway.
It's okay. Breathe.
Sonia from the Ontario Science Center. I'm glad you're here because we are gonna build a Rube Goldberg machine.
Really?
Yeah.
Oh my gosh, I'm so excited.
Yeah?
Yes.
I'm excited too. Check it out. This giant room. I've never done anything with it, so why don't we build a giant machine in here?
Why not?
Okay, so here's the rules. The Rube Goldberg machine has to start with one simple thing, right?
Yep.
So we're gonna start with this marble, and we send it on its way, and then a whole bunch of stuff happens, and at the end, we press that button.
That button?
Yeah.
What does it do?
I've never used it before, but when we hit that button, we get cake.
Cake?
A cake will portal in and we'll have cake.
Oh my goodness, can we get chocolate cake?
We can totally have chocolate cake.
All right, now I'm really, really excited.
Okay, so can I start?
Absolutely.
Great, because I saw some stuff over here.
Okay.
This is a pendulum. It's a weight that swings. It swings back and forth. Pendulums are pretty simple. It swings back and forth. Predicting the path of a pendulum, pretty simple. It's gonna swing back and forth. But wait, as I make it so much more complex by adding a pendulum. Now I've got a pendulum down here, and that one swings back and forth, and I've got a pendulum up here that swings back and forth. What will happen to this part of the pendulum when I let it go? Can you predict? Let's find out.
This is a double pendulum, and predicting the path of a double pendulum is really difficult. It's still simple physics, but because there's a moving part attached to a moving part, it makes it way more complex.
So, the question is, can we max it out even more? Of course we can. These are chaos pendulums. This one's a lever, and it's got another lever on the end. Whoa, and this one here is a perfectly balanced lever, and it's got a pendulum on either side. Whoa. Whoa. Scientists and engineers have always said that the more moving parts something has, the more complex they are. Science.
Sonia and I are taking turns building our Rube Goldberg machine. The first section was my turn, and I explained it to Sonia.
Right here, we have what is known as a ramp. Ooh, yeah, I know you know.
Fancy.
That. Right, so we put a marble on the ramp that rolls along this thing into what is known as a pylon. And then we've got these guys right here, which are dominoes. And when that falls off the table, it'll pull on the string, and then it's attached to this. Now, this is the release mechanism, so when that string gets pulled, it will let go, and it will fire this, which is a trebuchet.
All right, should we test it out?
Absolutely. You
Can
want
I
to try
try
it?
it?
Please.
Yeah.
Okay.
Okay, 3, 2, 1. Huh.
Wait.
Didn't go. Why didn't?
Well, the domino doesn't seem to be heavy enough to make this contraption fire.
You know what, Phil?
What?
I have an idea.
Oh, yeah?
Maxed out dominoes.
Maxed out dominoes. I love that idea. Why are they maxed out? Do they glow in the dark?
We'll see.
Do they produce electricity?
We'll see.
Do they talk to animals?
We will see.
Do they dissolve in water? Whoa, maxed out dominoes.
That's what I'm talking about.
These are very maxed out. Okay,
So
so
we
now.
started off with this domino. Then we went bigger.
Yeah.
Bigger, 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 bigger. And we went to the biggest.
Right.
And this is where we're gonna get the most weight, which is gonna trigger it and release.
Ha ha! Woo-hoo. Here we go. 3, 2, 1.
Here we go.
The one thing to remember about Rube Goldberg machines is they never work perfectly every time.
Didn't go.
But we tweaked it and adjusted things, and then...
Here we go.
3, 2, 1.
Nice. That was pretty far.
Yeah, check this out. Whoop. Okay, so
Nice.
now that we've got the trebuchet firing, and the ball is going over there, we need to get the ball going over here to
The
cake button.
cake button.
I can't wait for the cake. So I have an idea. Come on.
Okay.
No, wait. Changing direction stuff is over.
Okay.
Now we're gonna talk about tension. What's tension? One more than 9-shin. Get it? Because tension and 9, that's, okay, tension is the force that we usually talk about when we think about pulling a rope or a chain or something like that, because you know the old expression, you can't push a rope. But today we are gonna push a rope. I have a rope right here, and I'm going to push it using another force called flexion. I've got some pieces of plastic here, and they bend or flex. And when they do, they want to spring back. But I'm gonna prevent them from springing back by putting them in between these knots. And look, the rope now stays up. I take another piece, and I stick it on this knot, and then I bend it all the way. This is not terrifying. Really, it's not terrifying at all. Okay, good. And then I take this piece, and I put it here, and I bend it around, and so now we have a rope that's being pushed, and we're defying gravity, and we're making a cool art sculpture. All right, one more here. Ooh, okay, here we go. And flexing. And whoa. Ha-ha! There you go. I've pushed a rope, defied gravity, and made a cool art sculpture. Okay, well, I guess technically I haven't really pushed the rope because we're still pulling from each knot. And I guess I haven't really defied gravity because that one's sitting on the table and all the others are sitting on top of that. But you can't argue that I made a cool art sculpture. Ha-ha! Art! I mean, science.
Sonia and I are maxing out a Rube Goldberg machine. The first part worked pretty well, and now we need to change the ball's direction.
This is a trebuchet. Trebuchet fires the ball, right?
Yeah.
Right now I want to tell you the story of the ball. First, it goes through this fancy film of tin foil.
Aluminum foil?
Right, aluminum foil, because it's, yeah, you're right, it's made of aluminum. It enters this large receptacle.
A garbage can?
You also could be called a garbage can. It falls into this conular device.
Funnel?
A funnel, yes, you could call it a funnel. And then it enters the change-o-direction-o-matic, which is a lever. There's a weight on that end, then it falls off, then the ball goes this way.
Phil?
Or that way.
The one thing you need most of all when making a Rube Goldberg machine is patience.
Ball goes in the funnel, knocks that off, changes direction, and then it goes this way.
Okay.
And that's all I got so far.
So,
not bad.
Yeah.
But we really want to get closer to that way.
Right, because that's the button that gives us cake.
How about we use some chemical energy for this?
Ooh, chemical energy.
I have an idea for this one. Let me go get it.
Go for it.
This is my idea.
Okay.
Ball's actually gonna roll down the tube.
Oh yeah, because this is a rat trap, right?
Yeah.
Which is like bigger than a mouse trap.
And then it's gonna hit it. Yeah. Nice.
Ooh, so this flips around.
Exactly.
And what's this?
That is something called an antacid tablet. Some water.
And the antacid and the water react. Oh!
It blew. Do you want to test it out?
Sure, can I?
Okay.
Okay, ball comes through this, goes down there, comes out of this, and on the ramp.
Onto the trap.
Oh.
And
Ah! So then
Nice.
it fires up
Yep.
and hits something else
Yeah.
and something button cake. So we got a lot of different energies, but you know what one we're missing?
What?
Is electrical energy.
yeah, you're actually right.
I've got a great idea. Hold on.
All right. Let's see what he comes up with.
This is a chain of beads, and this is glass. Now, if I was to drop the chain of beads, what will happen? It will fall. Yes, that's right. It'll fall because of gravity. But watch this. This side goes up. Why? Because of gravity. Wait a minute. Why does one side go up because of gravity? Well, it gets a little complicated, but I can explain. But I think I'll have to put the beads back in the glass. Okay, so what's going on? Well, when this part of the chain starts falling out, it gets longer and longer, and it has more mass than this side of the chain. And if it has more mass, then it has more inertia. And when it starts yanking out very hard, this side of the chain gets yanked up out of the glass very quickly. And when it gets yanked up hard, it flies into the air. But then, of course, the direction has to change, so it goes around a curve and then goes back down. Because of the speed that it's going, that curve starts lifting up over the top of the glass. And that's how it works. There's a big difference in energy because this chain falls far. I try it from here, and it doesn't work as well. Why? Because the drop from here to here isn't as big. You want lots of force acting on the falling chain, which means the higher you do it from, the better it works. So maybe we should max it out. Yeah. But wait, we should wait for it to stop. And now let's max it out. This is a really long chain, and this is a really long drop. Let's see what happens. Whoa! Look at that. Whoa, super maxed out! Science! Sonia and I have used potential energy, the lever, and chemical energy. But you know what one we're missing?
What?
Is electrical energy. Electromagnetism. So watch. The chemical rockets, which we've had from before, they'll fire up, they'll hit the underside of this tray. The marbles will fall and flick this switch. See that sledgehammer?
Uh-huh.
This is an electromagnet, and it will attract the metal in the sledgehammer. Watch this, ready?
There.
There. Magnetized, electromagnetism. Now, when the marbles fall, it'll turn the electromagnet off, and the hammer will fall.
Oh, that's pretty cool, actually.
Right?
Can we
So
try it?
let's try it.
Here's something we didn't know. Predicting the flight path of an antacid rocket canister is almost impossible. We had them aim the same way every time. But we stuck with it, and being patient is key, and eventually it worked.
The chemical rockets fire, and they hit the tray. All right!
That's pretty cool.
Yeah, so now we just need hammer hit something, and then something, button, cake.
I have an idea.
All right. Cake any minute now. This is a basketball. It bounces. This is a golf ball. It bounces. But it never bounces as high as where I dropped it from. But watch as I put the golf ball on top of the basketball.
Whoa! Why does the golf ball bounce higher than where I dropped it from? How is this possible?
I only bounced the golf ball from 1 meter high. So what's going on? Well, as the basketball hits the ground, it compresses, storing the potential energy of its bounce, about to give that energy back as it bounces up again. But this energy works as a springboard for the golf ball. And since the golf ball has a lot less mass than the basketball, the upwards kinetic energy of the basketball is given to the golf ball. So, let's max it out. Ball, on a ball, on a ball. 3-ball bounce. Oh, did you see that? Ball, on a ball, on a ball, on a ball. Quadruple ball bounce. Oh, oh. Oh. No, wait. Turns out getting 4 balls to drop straight down on top of each other is pretty difficult. So, we know the mass of the ball is important. Why don't we max it out in a different way? This is a Swiss ball for exercising. It has a lot more mass than a golf ball. So, let's try it out. There you go. The transfer of energy between balls. A great way to lose golf balls.
Sonia has added one more step to our Rube Goldberg machine, a stomp rocket.
It's a hammer rocket.
Exactly.
I like
so
that.
what's gonna happen is the hammer is gonna hit our bottle, which is gonna release all that air that's built up inside of it. It's gonna hit that button.
Wait. The rocket hits the button.
And then we get some
cake!
Cake!
Oh, so this is it. So we're done the Rube Goldberg machine with this last step.
Okay.
Do you want to do it?
I think we should do it.
Ready?
Ready?
3, 2, 1. Oh.
Let's pause here just before the cake portal's in and recap the science. A marble on top of this ramp has potential energy. As it rolls down, that changes to kinetic energy, which transfers to some stacked dominoes. They fall in a chain reaction, finally causing bigger and bigger dominoes to fall, giving the last domino enough mass to pull a string, attached through some pulleys, to a quick release on a trebuchet. Now, a trebuchet is a first-class lever, with a weight on one side and a sling and a ball on the other. If the weight falls, the sling releases the ball at the right moment and it sails through the air. It's caught in a garbage can and changes directions on a few ramps and another lever as a teeter-totter. Finally, it falls onto a rat trap, which has more energy stored in the tension of the spring. The rat trap smacks another lever, which flips around, turning over some antacid rockets. This allows the antacid to mix with the water and start a chemical reaction that produces carbon dioxide, which eventually builds up enough pressure to fire the container to another lever, which tips, dropping some marbles on a string attached to a switch. That turns off the electricity to our electromagnet. And when an electromagnet doesn't have electricity, it stops being a magnet. So our sledgehammer starts to fall. Now, our sledgehammer is heavy, so it has both mass and speed when it hits this plastic bottle. All that inertia crushes the bottle, reducing its volume. The air gets put under pressure and pushes out through a tube, which takes our stomp rocket with it. The stomp rocket flies through the air and hits our cake button, which then portals in some cake.
Guess we really didn't think that through, huh? The cake should have landed on a table or something.
Would have been nice.
There you go, Science Max Experiments at Large, Rube Goldberg machine. Are you sure you don't want some of this cake?
No, let's
But
go. Let's go.